Hello guys. So today we're gonna work on the final exam project. So I am working with a groupmate, and my groupmate has done part one, and in this video I'm going to show you how to do part two. So it's basically 2D stimulation over a horizontal flat plate. It's 6 inches in length, and the thickness of the flat plate is 0.1 inches. So basically, to start this project, first we need to open the workbench. And when you open the workbench, just go to the geometry. Okay, so we have the geometry here. We just hit z-axis, and I'm gonna give this point. Okay, so basically I have sketched a surface here, and as in my previous videos I've shown how the sketching works. So I'm just gonna show my flat plate here. So this is my flat plate, and I have the length of this as well. So basically the horizontal length is gonna be 6 inches, and the width of the flat plate, which I chose here, was 0.006 inches. So that's gonna be very small as well. And I have placed this flat plate at the origin so that it's easier to calculate the boundary layer in order to calculate the graphs of at the midpoint at basically once we have the design, we have the sketch, you go to sketching, okay, you go to modeling, and then just hit sketch one. And sketch one, we're gonna go to concept, and we're gonna hit the surface from sketches, and that will create the surface here. So when you have this design in the design modeler, and also we're gonna make sure that the surface sketch has this sketch has a surface area and the volume, and also this surface is gonna have a thickness of 0.0254 meters, which is also mentioned in our project. That is, it's going to have the thickness of 0.1 inches. So in meters, it's going to be 0.0254. So when you have this design in Fluent, so we can see this design. It's going to look something like this. Okay. So we can see this flat plate. It's very thin because its thickness is like 0.1 inches. And the reason why I chose the slit to be really small, or my width of the flat plate to be really small, in order to get smooth results in the results section. So once you have this in Design Modeler, we're gonna go to meshing. So I'm gonna go to meshing. Okay, we have the mesh here. So in order to mesh, I always hit just right click, insert method, and then this automatic method is gonna get inserted in here, and then you just hit generate. And then I also hit right click, insert refinement, just to make sure that everything is smooth in my meshing, and I get better results in case of my velocity contours and velocity vectors. And element size here is 0.005. And when you hit both of this, when you do the method and the refinement, then you just hit generate, and this is going to generate a mesh like this. Name selections are really important. Those are critical for our boundary layer selections. So this name selection, this is the front of the horizontal flat plate. So front is basically, it's really small. So we gotta just let me just zoom in and show you the front portion. Yeah. So when you zoom in, this is going to be your front section, and similarly, the back section, the top section, and the bottom section of the flat plate. So that's the flat plate, but we gotta also determine the inlet, the outlet, and the symmetry on either sides of our design. So that's gonna be it. we did name selections, we meshed it up to 0.005 meshing. It really depends. We can also do 0.001 for better results, but 0.005 generally is good in order to get good results as well. So once we are done with meshing, we can just close this meshing part and then go to the setup section. Here. Yeah, and then we can just hit double precision, solver processes 2. Okay, so now once we have this mesh here, just gonna, okay, so first go to model, you gotta switch on this energy equation, then a flow is laminar, so we're just gonna hit viscous laminar, okay, and then we have to go to materials and we choose air, and density is going to be 1.225, but here I just for my better calculation purposes I just use 1, and viscosity I just use 0.0001. So you gotta make those changes and just change, create, and just close it. And then we're going to go to boundary. The back is going to be wall, the bottom is going to be wall, the front is going to be wall, and your inlet is going to be the velocity inlet, and that in the question here it's given 10 meters per second. So in the project also the velocity, the free stream velocity is 10 meters per second. So we get to hit apply and cancel, and then outlet is going to be a pressure outlet, and symmetry, let's just start symmetry, and the top is also going to be wall. So once we have all this done, we get to go to reference values, and we get to compare. Okay, so for the reference value, we just need to hit inlet, and then we can go ahead and start initializing. We can just do hybrid initialization. So initialize, and obviously console is here, so it says the initialization is done, and then iterations. So a number of iterations, usually it converges very easily, so number of iterations should be less than 100, and then you can just calculate. So, okay, perfect. So we have the results here. So first of all, we gotta create two surfaces in order to answer question. In order to answer part 2, part D. So plot the laminar boundary layer velocity profiles at 2 points, midpoint 3 inches and endpoint 6 inches on the flat plate. So how we can do that is just I'm gonna go to this endpoint, and then we're just gonna hit endpoint. Our starting is origin, which is 0, 0, and x1 y1 is 0, 0.0762. So that's just 3 inches. So it's from 0, 0 to 0, from 0, 0 to basically 0, 3. And this is I can start my starting point at 0, 0 because I place my midpoint of the flat plate on the origin. So it really depends on your geometry. So this point really depends on your geometry. And same we're gonna do with the midpoints. And then we're gonna plot. So we're gonna hit XY plot. And this XY plot is basically, first one is for the velocity, the X velocity with the curve length, and the point is the midpoint. We're gonna hit save plot. And this is our velocity versus curve length, and then this is the velocity versus curve length endpoint. So this is your endpoint. So this is going to basically answer your part D. For part C, what we can do is we can go here, we can go to reports, and then forces, and then you get to select all of them, and then print forces. So once they are printed, they're going to be in the console part. So Here we go. Okay, so this is the console part, and basically here it will give you all the addition of forces, and due to this viscous forces, we have our drag coefficient as 0.0036. So that's going to be your drag force coefficient here in this case. And then for answering the first part of question, which is get the velocity counters zoomed on the surface. So for that, we're just going to hit results. So when you go in the results section, so I already have this done. So this is what our velocity vector is going to look like. So what we just need to do is hit here vector, and when you hit vector, you say okay, and then you just choose the location. So your location is going to be symmetry 2 in this case, and then you just hit apply. So in that case, you will get the velocity vector something like this. This is zoomed in velocity vector. And in case where you want to get the velocity counter is just here. So you hit counter, you name it at velocity, and you hit OK, and make sure your location is symmetry 2. So when your location is symmetry 2, and counters, usually make sure it's something like 200, and then you hit apply, and then you will get the velocity counter as well. So here I already have it done. So what I'm going to do is I'm just going to say velocity counter. So this is my velocity counter along with the velocity vector. So let me just try to zoom out. So yeah. So this is basically my velocity counter plus velocity vector, and that is how we can answer the first part of the project. And the other calculation or the theory part of the project and everything is some theory and some plots are done in the Excel, and everything else is compared with the theoretical part, and it's about the same. It's not going to be the exact same value, but they're about the same. So yeah, that's it for this project.